Today we have 1 hour and 30 minutes. And so I prepared a presentation for approximately 40 to 50 minutes so that we can have a Q&A session. And if we have time also, I can make a quick demo of our software. And so I plan to first talk about the vision of the company. What are we aiming for? What is the end game of Grid Singularity? I will talk in detail about our product, which is an energy exchange as a service for energy communities. I want to talk quickly about the different market mechanism. How do we build energy community as a digital representation, considering the distribution grid as well as the different clearing mechanism. Then I will jump to how do we actually implement it in a software, including the different interface that we have to build more powerful strategies. And then I will conclude with showing some use cases and projects that we've been working on to show how the software can be used as a research tool, but also as a energy community deployment. So Grid Singularity is an energy startup based in Berlin and in Lisbon. We have 40 different members with a lot of different nationalities. We have a total of 24 different nationalities. A lot of people are also working remotely, which represents the decentralization that we are aiming for in the end. We are building energy markets as a service. And so what that means is that we are building an energy exchange software to deploy in energy communities so that participants like prosumers, consumers, and small producers can be empowered and become real actor in local energy markets. So they can trade, buy, and sell the energy they produce and consume on a local level, as well as on a wider stage. And while we're aiming this, we want to increase the degrees of freedom. So we believe that end users, they want to express their own choices and their own preferences towards energy. And so we are developing an energy market where we can tag an attribute on top of each bid and offers. And so that means that end user, prosumers can decide if they want to buy energy that was produced locally or in a nearby city. They can also choose what type of energy they are purchasing. So if they want PV energy that was produced from a PV, or if they want energy produced from a wind turbine, it's something that they can choose, as well as choosing from who they buy it from. So that could potentially create new social networks around energy communities where you have a group of people that want to trade between them. So for instance, I could buy the energy that was produced from my parents' PV installation, for instance. And an important thing is that while we are building this local energy market as a service, we want to be grid aware. So we're building this bottom-up market where multiple sub-markets can be stacked on top of each other based on the distribution grids. So as you can see on the picture, multiple houses can be grouped together behind one market that represent a substation or transformers. And so that they are incentivized to trade on a local level first. And then, of course, if they cannot be totally supplied by the neighbors, they can look to trade on a wider level. While we are building this energy exchange, we want to accelerate the energy market evolution. And so we believe that innovation can only be reached through a set of experiments and iterations. And so this is the reason why we built this 3-step program to deploy an energy community in the real world. So of course, the first step is a simulation, which starts by building the digital representation of the energy community. So it's placing the different houses on the market, adding the different assets, the load, the PVs, the batteries, uploading all the historical data. Then you can simulate it and optimize your local market. And so that simulation runs in a very fast speed, which allows you to tune different parameters and try to improve your community based on specific KPIs. Once the simulation stage is successful, we can jump to a canary test network, which was inspired by the canary in the coal mine. And this is basically a bridge between the simulation level and the real world deployment. And so it's basically a simulation that is running in real time using live data from real hardware. So instead of uploading historical data from CSV files, you would connect to a smart meter from the different homes or the PV meter or the batteries. And once we have a successful canary test network, we are satisfied by the stability of this canary test network, we can jump to a real launch of a deployed community into a real commercial operation. And so at the moment, we are building the technical requirements for this real deployment, and we expect to be done in the next year. We also believe that innovation and changes can only be done by connecting a marketplace to everyone and all the different stakeholders of the current energy market. And for that reason, we are focusing ourselves on building solely the exchange as a service. So meaning we build the spot markets, the flexibility markets, the settlement market, and the different clearing mechanism. And we also build the interface to interact with that software. So we have built an SDKs for grid operator and aggregators to interact and interface with our energy exchange. So on the grid operator API, which is obviously designed for DSOs and TSOs, they can interface with our markets by sending price signals to our exchange to incentivize specific behavior from the flexible assets. So with that API, they can basically use our tool as a congestion management tool. On the other side, we have the asset API, which was designed for aggregators. So those aggregators have as customer energy communities, prosumers, consumers, and small producers. And so they're connecting to their meter, so their live stream data, and they're interfacing with their clients through either a web dashboard or prosumer app, right? And so in the end, the energy community participants express their preferences, what type of energy they want to buy or to sell, what is the budget in terms of price they want, like the maximum price they want to pay for that electricity. And after that, the aggregator has to translate all of these preferences into an efficient trading agent. So whenever a consumer wants to only buy from a PV energy, then the aggregator will translate that into an active bidding strategy and send those bids into our energy exchange. And so, like I said, we are only focusing ourselves on the exchange and the interface that we're building. So I want to spend some time on explaining what are the different components that we have in the software and how they interact between each other. So when you arrive on a software, you basically have three main assets that are available to model your community. So we have a load, PV, and storage. So of course, the load can basically model an energy consumption. You can either upload your own data. So if you have historical data of your own building or own apartment, you can upload it to this digital asset. If you don't have such data, you can also use our average power tool, so-called, and that allows you to create your own profile. So you can stack up multiple devices depending on the consumption and the time of the day that they are active to build your own consumption pattern. We also have the PV, which is fairly similar. So it's a producing asset. You can upload your own generation if you have that data available, or you can use our template profile or use our Gaussian curve function. The last asset is the battery. It's different because it only takes as input the capacity in kilowatt hour, the minimum and initial SOC in percentage, and the maximum power of charge and discharge. So the battery doesn't take any profile as inputs because it's completely unbundled and behave depending on the market conditions. So depending on the price that is set on the market or the strategy that was set by the aggregators, the storage will charge or discharge. And all of these assets have trading parameters that I will jump to it later. We also have a markets maker, which is a very big important role in our software because it mimics the typical behavior of an energy utility. So if you have an energy community, the market maker will sell an infinite amount of energy at a fixed price. And we also implemented the infinite bus mode, where so that it's possible to simulate a feed-in scheme. So if your community have energy surplus from the PVs or other producing assets, this surplus can be sold to the grids at a fixed rate. Lastly, we have the market. And so like I said before, we are building a bottom-up hierarchical market. And so the role of this market is to group multiple assets or sub-market together. And so you can build multiple markets on top of each other to be grid aware. And so this is an example where we have at the top this grid market that is connecting the community to the wider grid. And then we have two different houses that are also markets in the end. And inside each of those markets, we have energy assets. So inside the market one, we have a load and a PV. And inside market two, we have a load and also a battery. And by building this hierarchical market representation that allows us to incentivize local trades. So for instance, if house one has some generation, it will first self-consume on the house level. So the PV will sell to the load. And if there is a surplus, then the PV will sell to the grid market, so potentially to the other house. And if, of course, if the other house cannot buy that energy, then the surplus will either be sold to the feed-in tariff if there is such a scheme, or it will be curtailed. And by having also this hierarchical representation, this allows DSOs to place granular grid fees on top of each market. So each of those markets can receive a different grid fees that you can see, which allows them to use it as a tool for congestion avoidance. And so this grid fee can either be set as a euro per kilowatt hour or as a percentage of the trade's price. And so you can either set it as a uniform value that is constant through the whole simulation, but you can also set it as a profile, which allows you to build more dynamic grid fee strategy to try to reduce the peak import or peak export of your community. Now jumping to the market mechanism. So this is obviously known. Market is divided into multiple time horizon. So you have the futures market, spot market, and balancing market. At the moment, we have our spot market that is fully operational. And we are currently building the futures market and the settlement market. And we expect them to be operational in the coming month. One thing that is important in a software is that the simulation and the spot market in the end are divided into time slots. So if you're simulating one day, so 24 hours, those 24 hours will be divided into multiple time slots where each asset will try to buy or sell the required energy. And the length of those time slots can be set as a parameter. So usually we set it as 15 minutes. That is based on the Europe spot market, but it can also be set for a length of 1 hour or even 2 hours, depending on the countries. And so inside during each of those market slots, the energy asset will have trading strategies. And inside the software, we have a template trading strategies that is very simple. It's a linear function where on the left, you can see the buying strategy from a load. So during the market slot, here it's a market slot of 15 minutes, but during the market slot, the load will first place a bid at a very small price in order to maximize savings. But if it cannot find any supplier for that price, then it will increase their prices until finding one. And obviously for the PV, it's the opposite. So you have they first try to sell at a very high price to maximize profits, and then they reduce their prices. And so then the idea is how do we match each bids and each offer together? So we have 3 different clearing mechanisms. The first one is the one-sided pay-as offer. So it's a single auction, so only offers are being posted on the market. And all the consuming assets will look into the market and select the cheapest offer. We also have a two-sided pay-as bid. So it's a two-sided auction. So you have both bids and offers that are being placed on the market. It's a continuous clearing mechanism. So that means that whenever there is a bid that has a higher price than an offer, they will get paired and matched together. And in that case, the trade price is the bid price. Lastly, we have a two-sided pay as clear. So it's also a two-sided market. And in here, it's an interval clearing where so the market is cleared only a specific number of time per market slot. By default, it's 3 times, but you can increase it or reduce it as you wish. And so the idea is that it's an order book where all the bids are sorted in a decreasing order and all the offers are sorted in an increasing order. And so when both curves are intersecting, it's set the trading price and the trading volume. One thing that I want to mention is that we are currently working on a matching API that allows you to create your own custom algorithm. And so you are not limited to those 3 clearing mechanisms. And we expect this API to be fully done end of the year. Now I want to jump to the implementation and explain a little bit the different interface that we have in the software. And we believe that it's only by being open source that we can drive innovation and acceleration in the energy market. And so this is why we have made the backend and our different SDKs fully open source. So you can go on GitHub and Grid Singularity and see the different repositories that are available. And they are all under GPL-free license. And that means that it's completely free to use for personal activities. If you're doing some research, a master thesis or a PhD, it's free to use. And the only thing is that if you use it for a commercial activity, then the rest of your product needs to be open source as well. So let's say you integrate part of our code into a bigger product that you sell, then the bigger product also needs to be open source under GPL-free. We also have a user interface that I've pasted a screenshot on the right, and that interface is private. So the code is not open source, but it's free to use. So I invite every one of you to just go on gridsingularity.com/singularityMap, and you can create a free account there. Once you created that account, you arrive on this big map. So you can see many different dots from different colors, so red, blue, and green. And so all of these different dots represent public simulation made by other users. Of course, if you want to make some simulation and you don't want to disclose the location of your energy community, you can also set it to private. In our user interface, we also have a step-by-step tutorial. So we are onboarding our user very smoothly, explaining what steps to take in order to build their first energy communities. We also have an express mode, which allows our user to quickly build their digital twin of their community. So we have template homes that are based on typical consumption profile and PV generation based on different location. So for instance, we have a template load for a student that has a job, a night shift job. We also have template consumption for a multi-generational house, a young couple that are both working. We also have template generation profile based on the location. So we have by default, I think 6 different cities that's for 1 kilowatt peak. And of course, when you are using those profiles, you can scale it to your own PV installation. So if you have a 10 kilowatt PV installation, you can just select the nearest city and then scale it. And so you are basically using those different components, building your energy community by placing them on the map and setting the different parameters that we saw previously. And once you've done, you can click on Run. And once the simulation is finished, multiple results are available. We have different KPIs, self-sufficiency, self-consumption, peak import and export of the overall community. We also have the savings, which is quite interesting because it calculates the potential savings of having a local energy market compared to a scenario without. So compared to a scenario where all the different community participants are solely buying the energy from their utility. We also have trades, volume, and profile. This one is my personal favorite. So the trades profile allows us to see which houses traded with who, how much energy they traded, and at what price. So all the different colors that you see here are different homes. On the top part is the homes that are buying energy on the market, and the bottom part is the homes that are selling energy. You also get different prices from the markets, so the minimum, maximum, and average prices, as well as the grid fees set by the DSOs. I said before that the backend is completely open source, and it also allows you to run a simulation only on the backend, so without the nice user interface. The backend is written in Python, so it requires our user to know that programming language to be able to interface and launch simulation there. It has all the new features, so it's when you download the backend, you get the latest changes that we've developed. The advantage of using the backend is that you get more freedom from it. So you can edit existing code if you want to add a new asset type, if you want to add electrical vehicle, for instance, or if you want to edit the current battery model. For instance, if you want to implement a loss function so that the battery is losing energy over time. This is all possible using the backend, where you can code your own model. And of course, you can contribute to an open source software if you wish to. For launching a simulation in the backend, it's quite different than the UI. You have to prepare a setup file in Python, where you build the digital twin of the community. So it starts with the different parameters, like the market type, so what type of clearing, if you're using the pay-as-bid or the clearing mechanism or other parameters. And then you build the hierarchical model. So for instance, here I had the grid market first, and inside the grid market, I had a community with different homes, like a family with 2 children that has a consumption and a PV. And yeah, and you set all the different parameters there. Then for launching, it's also different because we have to launch the simulation through a clear command. And once the simulation is done, you get results. So it's possible to get some plots in a HTML format. And you also get more details. So all the different bids and offers can be seen in CSV files format. And yeah, you get many results in a JSON format as well. One thing that I wanted to mention is how to contribute to an open source software. So there is actually 2 different ways. So the first one is if you found a bug. Since our software is open source, you can just go on the GitHub and click on the issues and see what were the issues that was already reported by other users. If you see that the issue that you've discovered are not reported there, you can create a new one with a title, clear description, and includes 3 paragraphs. So this is the process that we have to report bugs, which is by defining what are the steps to reproduce the bug, what is the actual behavior, and what should be the expected behavior. And in some cases, users are motivated to write the patch for fixing the issue. And so if that's your case, you can also open a pull request with your patch. And it's the same process. So just mention the clear description of the problem with the different steps to reproduce the bug, the actual behavior, and the expected behavior, and describe as detailed as possible your solution. The other way to contribute is if you want to add a new feature or change an existing one. And so for instance, if you want to add a new asset type, if you want to add electrical vehicles, heat pumps, or the clearing mechanism, you can submit your changes to us through an email. We will then review it if it's possible to integrate those in our software. And once you get a positive feedback from us, you can create a new pull request with your code, including a clear description of your feature. And at the end, we have our developer that will then review your pull request. And if they approve it, they will merge it to the online master version of our repository. One important thing to acknowledge is that if you contribute to our repository, you agree, of course, that your contribution will be licensed under GPL version 3. So all your features or issues that you're writing patch for will be made open source. So I said before that we are focusing ourselves on building the exchange and the interface. You saw, for instance, that some energy assets have their own limitation in terms of trading strategies or energy management systems. Like, for instance, you saw that the bidding and offering strategy is linear, which limits the optimization possibilities from the aggregators. And so for that, we developed the Asset API. And with that Asset API, they can actively manage multiple assets at the same time. So for instance, in this diagram, you can see that one Asset API was managing loads, PVs, and batteries from a whole community. I think in this case it was 70 assets in total. And that allows them to build more powerful strategies for energy management systems, so they can build better battery management, better demand side response strategies, as well as trading strategies of optimization. Also, from the DSO perspective, they have the grid operator that allows them to connect to multiple markets on different level of the grid. So in that experiment, we had a DSO that was connecting through one API to two different communities, markets, one zip code and one grid. And so they were able to gather different information, such as the volume that was being traded on those markets, the different prices or from the different trades from the markets. And in response, they are able to set a dynamic grid fees to try to reduce the congestion within the grid. And I want to finish by showing some use cases that we've done and project that we are currently working on to show how the software can be used in research as well as in energy communities. So we've done a study from a German community called EWS Schönau. The community was located in southwest of Germany. It was a community of 25 participants and with very diverse energy profiles. And the community was quite smart because they had a ton of generation. So 21 of the participants had PV generation for a total of 378 kilowatts of peak installed. 19 of the members had a storage with a total of 286 kilowatt hour of capacity installed. 5 of the members had a combined heat and power generation, and 1 of the participants was a very big prosumer. So you can see that this community had a ton of generation and ton of storage capacity. And what we did is different scenarios that we wanted to analyze for 2 different seasons. So we did 1 week simulation in May and 1 week in November. And so the reason was to simulate what was the pattern from the consumption and the weather that is changing between May and November. And we did 5 scenarios. The first one was to analyze and compare the impact of enabling local energy markets within a community. So we simulate the energy community without any local trade at first. So all the 25 homes were buying from their utility, and all the surplus of their PV were sold to the feed-in tariff scheme. And then we enabled the local trading, and we started to compare what are the benefits and the KPIs improvements once we enable the local exchange. We did a second scenario where we added electrical vehicles and wind turbines. The wind turbine was quite big compared to the size of the community, by the way. And then scenario 3 and 4, we did that optimization. So the goal was to see how much energy assets we have to add in order to allow the community to be fully self-sufficient. So how much PV capacity we need to buy, and how much storage we need to install if we want the community to be fully self-sufficient and operate in islanding mode. The last scenario was adding a new community nearby. So it was basically to see what happens if two communities start trading between each other, and if there is any benefits in allowing them to trade together. So I want to show how we model this into our software. First thing that I have to mention is that those screenshots are from our old UI. So like I said, we have this new UI, but unfortunately, those screenshots were not available on the new UI. But everything that I'm showing here are possible to model in our new UI. So that's why the color theme is different. But the idea is that we build the grid market at first that is connecting to the energy supplier and the feed-in tariff scheme. And then we had the version our community that is including 25 different homes. And inside each of those homes, we had the loads, PVs, CHPs, and batteries. And one thing that I want to mention is that the community had a 4-cent grid fees that we applied per kilowatt hour. And the idea was to account for the distribution grid usage. So if two houses were trading together, they had to pay 4 cents per kilowatt hour of grid fees for using the local grid within the energy community. Some results that I want to show. So the trades profile, that is so the same graph that I showed before. So like the positive part of the chart is the volume that is being purchased on the market inside the community. And the negative part is the volume sold. And so this is why you have this butterfly-shaped chart. And so at the start of the day, obviously, there is not a lot of generation within the community. So most of the houses are buying from the utility. But as soon as the sun rises, the PV starts producing electricity. And so you can see here all the different colored square, where that means that all the different houses were trading among each other. And then after sunset, there is less trade, and the only trades remaining are from the houses that had batteries. And so similar observation can be made from the prices here. So at the first start of the day, the prices was quite high because most of the participants needed to buy energy from the utility, so at the highest price possible on the market. And as soon as the PV were producing energy, it drives the price down for the community, and then it rises again after sunset. One interesting thing that we discovered is by looking at the storage behavior, so charging and discharging of battery of one of the homes, we discovered that when no local trades are enabled, so the storage is limited to the house generation. And I forgot for which houses it was, but in that case, the battery was not able to charge fully during the week. So multiple times it was only halfway charged. and and only one of the day it was charged at 100%. And when we enabled our local energy exchange, we saw that this storage can buy energy from other community participants, which allows it to store more energy. So instead of being charged fully 1 day a week, it was able to be fully charged 5 days a week, which was quite impressive to us. And by storing more energy, that means that the community self-sufficiency was increased by 5.7%. The self-consumption was improved by 7.7%, and the electricity bills of the community participants were reduced by 20%. And all 3 KPIs that I'm mentioning here are without adding new assets. So this is just by using the current infrastructure that they were having, and just by enabling our energy exchange software that we increased those KPIs. Another project that we did was a hackathon in the framework of Odyssey Momentum. It was held virtually, unfortunately, and it was in partnership with the Dutch DSOs, so Stedin, Allende, and Impulse, as well as Engie and E.ON. And so the idea was to optimize the energy bills from the community members, as well as reducing the congestion in the grid. So we had a total of 4 teams. 3 of them were using our asset API in order to optimize the trading strategy by placing optimized bids and optimized offers. And each of those teams were managing the asset for a whole community. So it was, they were managing 68 assets. And what was interesting is that each of those teams had a different approach. One of the team was using an optimization algorithm in order to place bids and offers on the market. Another one was using reinforcement learning approach. They were using actually a Q-learning agent. And the last one was using a decision tree algorithm. So this shows how the asset API can be used to build more powerful trading strategy in the end. So you just have to submit a bid and an offer on the market, but you can optimize it fully internally first. The last team was grouping the 3 Dutch DSOs that I mentioned before, and they were using the Grid Operator API. Their goal was to reduce the peak import and peak export of the community by applying grid fees. So they proposed 2 novel grid fees. One was called the Aziz reactive model, which is basically looking into the past, so taking into account what was the past imports and export of the communities, and depending on those values, raising or decreasing the grid fees. The second one was a time of use, but instead of changing the grid fees only once or twice per day, they were changing the grid fee every 15 minutes. So as you see here, this was the fees in euro per kilowatt hour that was changing throughout the day. So their strategy was to increase the prices during the day with a peak around noon to try to incentivize the other traders to avoid exporting the surplus of PVs at that moment. And then they were reducing it and increase it again during dinner time, so around 7 p.m. And so the grid fee profile was repeating itself every day. And the outcome of this hackathon, we had a peak import with only 1% reduced, which was not that quite impressive, but the peak import was reduced, peak export was reduced by 31%, which was really interesting. One last project that I want to mention is AI for cities. So we are doing a partnership with Rebase Energy to provide solution to cities to reduce their CO2 emissions. So there is different cities in the project: Helsinki, Amsterdam, Copenhagen, and other cities. And in that project, we are optimizing distributed energy resources. So by sizing the different assets, so the different PVs and the batteries, and also selecting where we should place those assets in those cities to avoid any congestion. And we are operating a local energy exchange in order to further increase the benefit of those assets. So to conclude, the Grid Singularity Exchange is providing a standardized API that allow new local energy services. So providers can connect to energy assets and start trading on behalf of them. Aggregators can connect to energy communities. They can manage those flexible loads, those batteries, optimize the trading, and enabling new business models in the end. Our tool can also be used by DSOs and TSOs to implement advanced grid fees as a tool of congestion avoidance. We're also building a marketplace for data and algorithm to provide further value to energy communities, as well as aggregators and AI companies. And so all of this is facilitated by the Grid Singularity open source software. And to finish, I just want to mention some useful links if you're interested. So feel free to register on our user interface. It's completely free to use. If you want to learn more, you can also check out our documentation. It's updated very frequently, as well as our Medium articles. You can also join our community Slack channel, where users are posting questions and also interesting papers about local energy markets. And if you have an energy community that you want to deploy energy exchange and with degrees of freedom, feel free to reach out to us by email at contact.gridsingularity.com. And yeah, that's it. Thanks a lot for the attention. And yeah, if you have any question, feel free to ask.
Thanks a lot, Chris.